working as Associate Professor in the Department of Electronics and Communication Engineering, St. Joseph's College of Engineering. Now, in this session, we are going to derive the input impedance of a dissipationless line. Input impedance of a dissipationless line. Now, what is a dissipationless line? Dissipationless line is one which has the resistance as 0. So, based on the values of R, we have two types of lines. One is called as line of zero dissipation and the other one is line of small dissipation. Now, we are going to discuss about a line of zero dissipation, which is nothing but a dissipationless line. So, for which the resistance R equal to 0 and the constants for the line of zero dissipation or the dissipationless line are L and C. So, these two are the primary constants for a line of zero dissipation, whereas here the value for R is 0 and conductance G is also 0. And then, so these two are called the primary constants for the line of zero dissipation. So, these are all the primary constants. And the secondary constants for the line of zero dissipation are R0 and gamma, where this R0 is going to be, it is root of L by C, and gamma is, it is imaginary, which is alpha plus j beta, and for a line of zero dissipation, it is purely imaginary, which is j beta. Here, for a line of zero dissipation, there is no attenuation, so alpha is 0. And the voltage and current equation for a line of zero dissipation are, the voltage and current equation for a line of zero dissipation are written as E is equal to ER cos beta S plus J IR R0 sin beta S, and I is equal to IR cos beta S plus J ER by R0 sin beta S, where beta is 2 pi by lambda. And here for a line of zero dissipation, now these two equations are called the voltage and current equations. So, now we are going to derive the input impedance of this dissipationless line or line of zero dissipation. You consider a finite line. Consider a finite line of length L. Here, this is the input side. So, this is the input side, and here you have the output side, which is terminated by an impedance of ZR. So, this is a finite line terminated by ZR, which is an unknown impedance. So, here you have the input side and we are going to find out the impedance at the input terminals of this dissipationless line. And now, here let us define the input impedance of this dissipationless line. So, input impedance is nothing but it is the ratio of the input voltage to the input current. So, this input impedance, it is also known as the sending end impedance, because in transmission line theory, here you have the input side which is called as the sending end and the output side is called as the receiving end. So, here the voltage across the input terminals is designated as the sending end voltage ES, and the current at the input terminals is designated, or at the sending end is terminated as, it is designated as IS. Now, our aim is to find out the input impedance, which is nothing but the sending end impedance for this dissipationless line. So, which is defined as the ratio of ES to IS. So, sending end voltage to sending end current. Now, how do we find out the sending end voltage? Now we need to apply the boundary condition in the equations of voltage and current for a dissipationless line. So as we see that the current voltage equation is E is ER into cos beta S plus J IR R naught sin beta S. Now what is this S? S is the distance which is measured from the receiving end to the point of observation. Now let us assume that here is the point of observation and this distance is taken as S. Actually, this is for the general case. Now, specifically here we are going to derive the input impedance, which is the sending end impedance for a dissipationless line. Now, here we need to apply the condition. At S is equal to, at this point at the receiving end, the value for S is, it is 0. Now, when you move towards the generator or towards the source, at the sending end, the value for S is equal to L, because the length of this line is L. And now you apply this condition. At at S is equal to L, what is E? E equal to ES. So at S is equal to L, E equal to ES, and at the same time I is equal to IS. So now let us find out ES. So what is ES now? It is ER cos beta. Instead of S you have to write L plus J IR R naught sin beta L. Similarly, sending end current is written as IR into cos beta L plus J ER by R naught into sin beta L. Now, to find the sending end impedance, divide ES by IS. So now let us divide ES by IS. So divide ES by IS so that you will get, now ES is ER, the receiving end voltage, into cos beta L plus J into IR R naught sin beta L divided by IR cos beta L plus J ER by R naught sin beta L. Now from this we can write this ER as, ER is product of IR and ZR, so that IR is common in the numerator, and here also we can write ER as IR into ZR. So it is IR into ZR, so that IR is common both in the numerator and in the denominator, so that this equation is now reduced as ZR cos beta L plus J R naught sin beta L divided by cos beta L plus J ZR by R naught into sin beta L. Next step, here in the denominator we have an R naught. So you take R naught as LCM, so that this R naught, it goes to the numerator. Therefore, we can write, this implies this ES by IS is, this is nothing but now this is ZS. So I can write the sending end impedance as, now this R naught, it goes to the numerator. So therefore it is R naught into ZR cos beta L plus J R naught sin beta L divided by, when you take LCM, the denominator you will have R naught cos beta L plus J ZR sin beta L. So this is the expression for the sending end impedance of a dissipationless line. So here it is R0 into ZR cos beta L plus J R0 sin beta L by R0 cos beta L plus J ZR sin beta L. So this is one form of writing the sending end impedance. So there is another form of writing the sending end impedance. So where you can divide the numerator and denominator by cos beta L. So that you will have Zs as R0 into Zr plus J R0 sin beta L by cos beta L is tan beta L divided by R0 plus J Zr tan beta L. So this is another form of writing the sending end impedance of a dissipationless line or for a line of zero dissipation. So once we find the input impedance or the sending end impedance of a dissipationless line, our aim is to derive the impedance, input impedance of a short circuited and an open circuited line. So now we are going to derive the short circuited impedance and the open circuited impedance. Now you consider a short circuited line. So what is the short circuited line? Short circuited line is one whose terminating end impedance or the receiving end impedance is 0. Short circuited line. Consider a finite line of length L. So here the line is terminated by an impedance ZR which is equal to 0. So this is called as a short circuited line. So now the corresponding sending end impedance is now designated as the short circuited impedance ZSC. So when a line is terminated by 0 or when a line is short circuited, the input impedance or the sending end impedance across the input terminals is designated or called as short circuited impedance. Now let us find out what is the sending end impedance for this short circuited line. So the condition is here. We know this is the equation for the sending end impedance of a dissipationless line. Now in this equation you substitute ZR equal to 0. So now for a short circuited line ZR is 0. So this implies the short circuited impedance ZSC is equal to, now it is R0 into the first term ZR is now 0. So 0 plus J R0 tan beta L divided by R0 plus J ZR is now 0 into tan beta L. So we get the short circuited impedance as, here in the denominator we will have R0. So R0 gets cancelled and therefore the short circuited impedance is found to be J R0 tan beta L. So this is the equation. So this short circuited impedance, it is found to be purely a reactive one. So there is no real part in this short circuited impedance. So it is purely reactive. So that this implies that since the reactance is positive, so a short circuited line, it can offer an inductive reactance. It is inductive reactance. So next one is open circuited line. So the open circuited line is one whose terminating end impedance is very high or infinity. So open circuited line is one wherein ZR equal to, ZR is infinity. Consider a finite line of length L. Here leave the terminating end as open circuit, which is ZR is very high, it is infinity, and the corresponding impedance at the sending end is now designated as ZOC. So this is ZOC. Now to find out ZOC, in the equation of the sending end impedance, so we know that sending end impedance is, it is R0 into ZR plus J R0 tan beta L by R0 plus J ZR tan beta L. So before substituting ZR equal to infinity, divide the numerator and denominator by ZR, so that this expression becomes R0 into 1 plus J R0 by ZR tan beta L by R0 by ZR plus J tan beta L. So therefore, now you substitute ZR equal to infinity. So this implies ZOC is equal to, now it is R0 into 1 plus J R0 by infinity into tan beta L by R0 by infinity plus J tan beta L. So R0 by infinity is 0. So the numerator, we will have R0 into 1. The second term becomes 0 divided by the denominator. First term becomes 0 and you will get 0 plus J tan beta L. So which is R0 by J tan beta L. 1 by J is, it is minus J, it is R0. 1 by tan beta L is cot beta L. So therefore the open circuited impedance is found to be minus J R0 cot beta L. Here also, for an open circuited line also, the impedance is found to be purely a reactive one, and it is found to be a capacitive reactance. So from this we can conclude that a short circuited line, it can contribute only an inductive effect, it contributes only inductive reactance, whereas an open circuited line, it contributes only capacitive effect, it provides capacitive reactance. So this is about the input impedance of a dissipationless line and for an open circuited and short circuited line. Now we will derive the input impedance of a lambda by 4 line. So a lambda by 4 line is a quarter wave line, or it is called as quarter wave transformer. In order to derive the input impedance or the sending end impedance of a quarter wave line, we will write the sending end impedance of a dissipationless line. So we know that ZS is R0 into ZR plus J R0 tan beta L divided by R0 plus J ZR into tan beta L. So now starting from this equation for sending end impedance, let us derive the sending end impedance for lambda by 4 line. What is a lambda by 4 line? A lambda by 4 line is one whose length is lambda by 4. So now L is lambda by 4 and this line is also terminated by an impedance ZR. Now we are going to find out the impedance across the input terminals of this lambda by 4 line. So let us find out tan beta L. So tan beta L is tan into beta is the phase shift constant, which is 2 pi by lambda into L. Here length of this lambda by 4 line is lambda by 4. Lambda gets cancelled and 2 and here it gets cancelled. We get tan pi by 2. So tan pi by 2 is this infinity. So before substituting the value for L as lambda by 4, we will divide the numerator and denominator of this equation by tan beta L, so that we get the sending end impedance as R0 into ZR by tan beta L plus J R0. Denominator, we will have R0 by tan beta L plus J into ZR. Now, for lambda by 4 line, tan beta L is found to be infinity. So now you can substitute tan beta L as infinity. So R0 into ZR by infinity plus J R0 divided by R0 by infinity plus J ZR. So anything divided by infinity is 0. So therefore, for lambda by 4 line, the sending end impedance is found to be R0 into J R0 divided by J ZR. Here J gets cancelled. We get the sending end impedance as R0 square by ZR. So the sending end impedance for a lambda by 4 line is found to be R0 square by ZR. So this is the final equation for the sending end impedance of a lambda by 4 line. Similarly, we can derive the sending end impedance for a line of length lambda by 2 as well as a line of length lambda by 8, and we can see the discuss the application of each line. So now let us discuss the application of this lambda by 4 line. So this is the sending end impedance for a line of length lambda by 4. So this is nothing but a quarter wave line or quarter wave transformer or lambda by 4 line. Application of this lambda by 4 line, the first application is lambda by 4 line can be used as an impedance inverter. What is an impedance inverter? An impedance inverter is one which can transform a low impedance into a high impedance and vice versa. Here the sending end impedance for a lambda by 4 line, it is found to be R0 square by ZR. When you consider a short circuited line, the receiving end impedance is 0. So the corresponding sending end impedance is now, it is found to be R0 square divided by 0, which is nothing but infinity. So this is applicable only for the case of lambda by 4 line. So this is an important application of lambda by 4 line because it can only transform a low impedance into a high impedance. Similarly, it can transform a high impedance into a low impedance. That means when the receiving end impedance is infinity, the impedance across the input terminals of the lambda by 4 line is found to be 0. So it is L is equal to lambda by 4 and the open circuited impedance, it is now found to be 0. So that means when ZR is infinity, ZS is, it is R0 square divided by ZR is now infinity. Substitute so that you will get ZS as 0. So this is known as impedance inverter. So an impedance inverter is one which can transform a low impedance into a high impedance. The second application of this lambda by 4 is it is used to couple the main transmission line with the load. Here the load is nothing but an antenna. So a lambda by 4 line can be connected between the main transmission line and the load to match the load impedance with that of the source impedance. So this lambda by 4 line can be used as an impedance matching device. So it is one of the impedance matching devices. So by matching the load impedance with the source impedance, the maximum energy or maximum power can be delivered from the source to the load. So this is about the input impedance of a dissipationless line and the input impedance of a short circuited and open circuited line, and we have also derived the input impedance of a quarter wave line and discussed about the application of the quarter wave line. Thank you.